Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. It's my great pleasure to introduce Charlie Rice, who's a PhD candidate from University of Washington. His advisors are Hank Levy and Steve Gribble. And Charlie has done a lot of work on securing the web, whether it's securing the browser or securing the web services or investigating, the bad things that ISPs may do to people. So Charlie's going to interview with both the security and the networking research group. And he's going to talk about his experience of building a safer web.
Thank you, Helen. So, hello. Thanks for having me here today. As Helen mentioned, I'm going to talk today about some of my dissertation work to try to make it safer to browse the web for what it's actually being used for in many cases today, which is running program code. And this includes projects both to try to improve web browsers and web content to make them more robust and more secure against some of the problems that we're seeing today. So my work is motivated by the fact that the web has really changed significantly over the last decade or so. That we're no longer just looking at static documents that need to be rendered by the browser. We're looking at active programs that are running within the browser itself. Things like webmail clients that have significant complexity on the client side, but that are written in languages like HTML and JavaScript code. And so they're running right inside the browser itself. Now, this ends up putting the browser in a new role, something that it wasn't necessarily designed for, which is sort of like an operating system. It has to run these independent programs side by side and prevent them from interfering with each other or causing damage. But browsers weren't architected for this to begin with. They were sort of designed for rendering documents. And web content also isn't really designed for expressing programs. It's designed for expressing a marked up document. So publishers also face real challenges in trying to get programs to run in this space. So before I dive into any of the problems here in any detail, I wanted to just give you a sense of the types of contributions that I've had in this space. So I've worked on a project to build a new type of browser architecture using multiple processes in an effort to prevent interference between programs. And this will appear at the Eurosys conference next month. I've also done a study to see how web pages are changed between the server and the client's browser using a mechanism called a web tripwire. And that appeared at NSDI in 2008. I've laid out some architectural principles for what we might need to do to have better support for programs within the browser. That was at the Hotnets workshop in 2007. And I've done some work to try and prevent cross-site scripting attacks and browser exploits using a whitelisting mechanism for JavaScript code at UW, and then a research prototype called BrowserShield here at Microsoft Research, which interposed on web content. And that appeared at OSDI in 2006. Now, in this talk, I'm just going to focus mainly on these first two projects. But that will give you a sense for some of the things I've done both on the browser side and on the publisher side. But I also want to point out just the range of different types of projects that this represents. So it ranges from the more concrete side to, with the browser architecture project is code that's actually deployed in Google Chrome today, to a measurement study looking at 50,000 different web clients and how their views of web content change. But also a position paper and two research prototypes, including a prototype that we've recently seen has gone on to help influence the Live Labs Web Sandbox project, which we were excited to hear about. OK, so all of these projects are united in the sense that they're trying to do a good job of supporting complex program code within the browser itself. And in that sense, it's acting like an operating system. So we can sort of take a step back and consider how operating systems do this today. What sort of properties do we have in a platform that's been thinking about this for a long time? So you might have lots of programs running side by side. And we have things like performance isolation between these programs. So if one of them slows down or locks up, you can continue using the other programs on your desktop. We have good resource accounting. So we have things like the Windows Task Manager that can tell you how much CPU and how much memory your programs are using, and you can diagnose problems when something goes wrong. We also have failure isolation, in that if one of these programs crashes or becomes corrupted, you can throw out that program and its address space and continue using the rest of your programs, that it doesn't necessarily interfere with the other programs that you're using. And all of this gets at the fact that we have a clear program abstraction within the operating system. We have some sense of what code and data are related, and we can load them in separate processes. We have mechanisms that support that. Now, if we move over to the browser world, it turns out we have to give all of that up. We're still running programs side by side. We still have things like webmail clients and video applications, other services you might be using. But now we've given up things like performance isolation. So in many browsers, if something slows down in the browser, the whole browser locks up in a way, and you're unable to interact with other programs that you're using or the browser's user interface itself. We've also given up good resource accounting. So there's no task manager that can tell us which one of these programs is to blame if the browser's slowing down. We just see that, oh, geez, Firefox is using 90% of my CPU again. And you have to sort of guess which one is to blame and go hunting and pecking, closing tabs. We've also given up failure isolation, that if one of these programs triggers a bug in one of the rendering engines or the plugins, the runtime environments of these programs, you can end up losing the entire browser and all the programs that you're working on. So in that sense, we don't have good support for programs. And in fact, we don't even know really what a program is in the browser. You might think it's something like a page or a window, but it's not really that in all cases. So you might look at this example of Gmail, where you've got a Gmail window, but then you've also got a chat window and a tasks window and a composition window that have all popped out from there. And in many cases, you can use some JavaScript code to pop those things back into the window. They're all very tightly integrated and part of the same program. But there's no abstractions in the browser to capture this. We just sort of have sets of windows and pages. So what we need to do is find a way to build up those properties that we had from the operating system world and support them again for these programs on the web. So my thesis here is that we can actually learn from some of the things that we've developed in the operating system world and use that to improve the browser and web content to provide a safer platform for running programs. And we've laid out 4 different architectural principles in our hotness paper to try and get at what's required for this. And these include defining exactly what a program is within the browser, the precise program abstraction, being able to isolate these programs from each other in the browser's architecture so that we don't get that sort of interference that we saw, making it possible for publishers to authorize what code gets to run in their own programs so they can reason about what their programs do, and then having ways to interpose on program behavior so you can enforce policies that you didn't anticipate to begin with when the web was first designed. So in the rest of this talk, I'm going to focus on 2 of the projects that I've worked on, primarily ways to improve browser architecture. And this is work that is appearing in the Google Chrome browser, which is also called Chromium. That's the open source browser that shares the same code base as Chrome. And it includes finding program abstractions within the browser and then isolating them from each other. After that, I'll give you a briefer overview of our web tripwires study about how content is changed between the server and the browser, touch a little bit on the previous work that I've done, and then conclude with some future directions. OK. So we're trying to do a better job of supporting programs within the browser. So the best way to start here is to sort of look at an example about how someone might use their browser. So consider a case where you're looking at a webmail client, and within there, you use some integrated functionality to pull up a list of documents and a document that you're working on within the browser itself. And there's lots of suites that can do this. There's Zoho, there's Google Docs, and so on, where you're actually editing things within the browser itself. Now, while you're working on one of these documents, maybe you pull up a second one from your document list, decide that you don't need that right now, and you navigate that to a different website, like a blog. Now, this is already something different from the operating system world, where you can take an existing window and navigate it to a completely different program. While you're here, maybe you get distracted and you start reading a news website, pull open an article in another window, and then while you're working on a mail message, you pull up a second copy of your mail client so you can read a different message while you're writing one. So I don't know about you, but my desktop looks like this pretty much all the time. I always have lots of windows open. Some of them are related to each other. Some of them aren't. And the key point here is that we've got several independent programs that are running side by side here. Now, in many of today's browsers, we end up with a monolithic architecture that puts all of these programs in the same process. So that's where we get things like poor performance isolation, poor failure isolation, even poor security if something went wrong in one of these, where if something does go wrong, it can spread to the rest of the browser. So we should do a better job of architecting the browser to prevent these things from happening. So how might we do that? We'd want to carve it up so these different programs are running in different processes, for example. So maybe we create a process for each window in the browser. Now this is nice because we would get some of those benefits back. We'd get performance isolation and failure isolation. But the trouble here is that we'd end up breaking some pages that do directly communicate. And that the Gmail window and the chat window is one example. Maybe the document list and the document are part of a single program and they're talking to each other with JavaScript. And by talking to each other in the browser, I mean they actually have shared access to each other's data structures, each other's functions. It's very tightly integrated. And it can only happen in certain cases. It can happen when pages are connected to each other, so they have some handle to refer to each other's contents. And it happens when they're from the same origin, so the browser allows them to talk to each other. But because the process per window approach doesn't reflect that, it sort of fails as a program abstraction. It doesn't capture what we think of as a program, like a document editing program that has multiple windows, or the Gmail program. And it can break compatibility with pages that do interact in a tight fashion. So we're after some sort of program abstraction that can capture these constraints. We want something that will match our intuitions about what a program is on the web, as well as preserve compatibility so that pages that did communicate before can continue to communicate. And we'll see that we can get there by taking some cues from the browser's existing rules and mechanisms about how pages communicate in the browser. And then we can isolate these groupings in separate OS processes to get that isolation that we're after. And I'll show that we can get performance and failure isolation in this, with the abstractions that we get, but not necessarily secure isolation of sites from each other. And that's because in this project, we were very focused on preserving compatibility as one of our constraints. So we were looking at getting this into a browser like Google Chrome that we could put out on the web today and be able to support content that's out there. So we're focusing on compatibility a little bit more than security in this situation.
Do you think the compatibility and security are always in conflict?
I don't think they are necessarily mutually exclusive. I think that you will often have to give up some of the things you'd like to get to be able to support the content that's out there. And it'd be nice to change these things. But given the amount that's out on the web today already, it's tough to change everything. Yes?
So far you've been sort of separating, at the page level, what about situations where you've got multiple applications within the same web page, like a mashup or a gadget embedded in a page?
Sure. So there are situations where you do have mashups, multiple applications in the same page. I think that that's also a good opportunity to look at how you want to isolate these different applications from each other and allow them to communicate. And I think there's been some great work done in this space. For example, the Mashup OS project has tried to expose communication abstractions for these different communicating applications within a page. That's not something that I'm going to get into here, but I think that's also a very important direction for supporting programs. OK. So first, I'm going to talk about how we can find program abstractions within the browser, then how we can isolate them from each other, and what benefits that gives us for robustness and performance. So at a high level, we're looking for some sort of abstraction that represents a program in the browser. And that's what I'm going to call a web program. It's some set of pages and the sub-resources for those pages that make up a common service. And this is just like in the desktop world where you have code and data that makes up some application that you're using. Now, we also need an abstraction for an instance of one of these web programs, which is a live copy of that running within the browser itself. And you may have multiple web program instances of the same web program in a given browser. For example, the 2 copies of that webmail program. Now, the important thing here is that this is the unit that we'll end up isolating within the browser's architecture. We have some web program instance that can run in a process. Now this is intuitive, but it's vague. This isn't something that the browser can look at and say, oh, okay, I know what a web program instance is. We need to figure out how to define this. Yes?
So would there be any sharing between the web program instances?
There will be certain types of things shared. For example, they share the same set of cookies from the same website. And I'll touch a little bit about how strongly they can be isolated. But they won't have direct access to each other's contents.
Can you do navigation across different instances?
Navigation, so you can have a web program instance and then navigate to a new web program instance. So if you're looking at two different web programs, you can navigate between them. But then they would be separate web program instances. OK, so let's look at how we can define these in a more concrete sense. And specifically, we want to find abstractions that are compatible with the content that's out there on today's web. And what we found is that there's 3 different ways that you could actually carve up the content within the browser to put them into separate processes and isolate them without breaking pages. But they're going to match our intuitions about what a program is to various degrees. Some are better than others. So first, we could look at the browser's access control policies. We could look at things like the same origin policy that says that if 2 pages are coming from different origins, they're not allowed to communicate. So maybe we can isolate them in separate processes. We can also look at the communication channels between pages and come up with what we call a browsing instance abstraction, where only pages that have handles to each other and are allowed to communicate, and have the ability to communicate, need to be in the same isolation unit. And if you don't have a handle, then maybe you can put that in an isolated unit. And what we'll find is that neither of these capture quite what we want with a program. We actually want the intersection of these two. And this is what we'll call a site instance, which is where we're headed. So I'll explain a little bit more about how we define each one of these abstractions. So first, we can look at the access control rules in the browser. This is where we get a site abstraction. So the same origin policy says that 2 pages are allowed to communicate if they come from the same host, protocol, and port, which is the origin. So for example, the 2 pages here from docs.zoho.com can access each other's data structures, call each other's functions. Essentially, they're running in the same address space within the browser. But the pages from different origins are not allowed to communicate with each other. Except it's not quite true. There's actually some ways to bend the rules here. Pages can modify a variable in their own namespace called document.domain. And the browser will then change how it views these pages in its access control rules. So a page can change its document.domain to drop off some of the subdomains. So you could say, rather than treating me like docs.zoho.com, treat me like zoho.com. And the mail example could also do that. And in that case, all of these pages from zoho.com could communicate with each other. So we don't want to break pages that are using this already. And as it turns out, Zoho is one of these pages that uses this today, as is CNN, as is MySpace. There's cases where pages from different origins do end up communicating with each other, even if they're just coming from the same site.
Do you feel this is more of a browser's legacy of lack of communications in the past? But now, we have, like post message existing in today's, recently released browsers in IE8 as well as in Firefox. I'm not sure about Chrome. So do you think, do you think this kind of domain setting subdomain-based usage is? Do you feel that? I think that's actually a core practice. Do you think those will go away? Or? I'm
hoping that they will go away. I'm hoping that having better communication mechanisms between pages will allow pages to not rely on this feature as much. I think that it's difficult to require websites to use those channels today, particularly because so much of the web-using population is still using older browsers that don't support those features yet. And in those cases, you do still need to rely on some of these.
So what are some of the things that they're communicating to? Can you give some examples of how they use these today?
That's a good question. I don't have a lot of specific examples off the top of my head. I know that, for example, that you might end up passing updates between the mail and the document program if something changed there. I'm not sure. I think some of the CNN examples might have frames that communicate across, even though they're hosted on different origins. But I don't have this off the top of my Okay, so thankfully there's at least a limit to how much pages can change their document.domain. And that's up to the registry-controlled domain name. This is the part of the domain name just before the .com or the .co.uk that is essentially identifying the website that it's coming from. And so what we can end up with is a site abstraction that represents the registry-controlled domain name plus the protocols, whether it's HTTP or HTTPS. And pages from different sites will never be allowed to communicate with each other based on the same origin policy. So we can end up with 3 different sites in this example, one for Zoho, one for Blogger, and one for bbc.co.uk. And we could put these in isolated units, and they'd never be able to access each other's contents. So that's one approach. It's the first proposal we've seen that doesn't end up breaking the content that's out on today's web. But we can do better than this, because in this case, we end up putting everything from Zoho.com in the same process, even if you have independent copies of your mail program that aren't going to be directly communicating with each other. And if you have lots of copies, they may end up interfering with each other performance-wise and so on. So we can do better than this. So second, we can take a look at the communication channels between pages within the browser. And this will give us what I call a browsing instance abstraction. So we can recognize that not all pages in the browser can talk. You need a handle to another page to be able to access its data structures. And those handles come about as a result from the relationships between windows in the browser. Sort of interesting, it depends on how you got to the page, in a sense. So because the document list opened these 2 documents using JavaScript code, using something like window.open, it has a handle to it. And it can say something like, this w gets window.open, and so it has a handle to this new child window that it just created. And the child windows can also talk about their parent by saying something like window.opener. Now the interesting thing here is that this is a property of the window, the container of the page, and not the page itself. So it outlasts the lifetime of the page. So remember, we navigated this window to a different website entirely. But it can still talk about window.opener. It's just that the same origin policy won't allow it to reach into the content of that page. It can only do things at a very high level, like maybe navigate that window to a different website, or possibly traverse the frame hierarchy within that window. But the same origin policy won't let it do anything more fine-grained. So in that sense, we end up with a set of connected windows within the browser. And we can call this a browsing instance. And we can look at all the different sets that have references to each other. And we can put these in isolated units, because pages in different sets won't be able to communicate with each other directly. Now this is also not something you'd want to use as a program abstraction, because it ends up conflating pages from different websites that are clearly not related to each other and won't be able to communicate based on the same origin policy. So we can finally end up with this site instance abstraction that goes for both of these properties. It's the intersection of a site and a browsing instance, and it's a set of connected pages from the same site. So it reflects that the browsing instance here, pages from the same browsing instance and the same site are in the same site instance. And it's always safe to isolate things in the site instances from other site instances, because either it's in the same browsing instance but from a different website, so the same origin policy says, no, you can't talk to it, or it's from the same site and different browsing instance, so there's no ability, there's no channel to talk to the other pages. So this is what we use as our compatible notion of a web program instance. Yes?
What if in the blog window I end up going to a Zoho site? Or maybe the blog window itself references some, or part of it is running a program on Zoho.
That's a great question. So if you start navigating these windows to a different site, those windows will need to reflect the site instance of their parent, of the site, the page they're showing. So this window actually started out in this site instance when it showed a document. When we navigate it to the blog, it'll switch to a new site instance for the blog. And if you went back to the Zoho site, it would have to go back to this existing site instance, because there's a reference and it could now talk to each other's contents. So that brings up a point that there's only ever one site instance per site within a browsing instance. For example, you couldn't have 2 Zoho site instances within that browsing instance. OK, so just to recap these, we have a site abstraction that says where pages come from, a browsing instance abstraction that captures how windows in the browser are related to each other regardless of what site they're showing, and a site instance abstraction that captures the connected set of pages from the same site.
So let's consider a specific scenario where you visit, for example, attacker.com, in which you have a CNN iframe, and from the CNN iframe, you open the CNN tab. Are these all in one process or different process?
So this is a good question. The way iframes work, in an ideal sense, when we're talking about these abstractions, an iframe is an independent page and should be treated independently of its parent. So that CNN iframe inside attacker.com would ideally be considered a separate site instance running in a separate process that would share a process with the new CNN tab. We'll see that in the implementation of this, we haven't quite gotten there in the Google Chrome implementation. So I'll talk about that more later. OK. So we did have to give some things up to get here.
Sorry, following that example, you said there is a CNN subframe inside the attacker.com suite. And there's a new tab that's also CNN.com. Are these CNN.coms two site instances or one site instance?
It depends on whether they're part of the same browsing instance. So if that iframe opened a new CNN tab, or if something else in the same browsing instance opened a new CNN tab, they'd be part of the same site instance. If you got to that CNN page independently, then it's a separate site instance. Thank you. OK, so what did we have to give up to get here? Turns out this is somewhat of a coarse granularity. That if you noticed, we ended up putting one copy of the mail program in the same site instance as the document program, even though intuitively those are sort of independent of each other. And that's because we do need to preserve the fact that sometimes those pages will end up communicating. The browser let them, and they could do that by changing a document.domain variable. Now, thankfully, because we can put separate instances of web programs in different isolated units, that'll help provide some isolation that we wouldn't otherwise have gotten. There's also some imperfect isolation. As Helen asked earlier, there's some things that are shared between site instances. Cookies is one example. If you pull up a second copy of your webmail client, you're still logged in. So they're still sharing the same set of stored credentials in the browser. But they won't be able to directly access each other's contents.
Do you feel that's imperfect? Or you think that's so for example, even the two program instances in today's desktop programs, two program instances of a program, they share, they can access the same files.
Yes.
Right?
So
that seems to be reasonable.
I don't think that this is necessarily something that needs to change. I think there's room for improvement here. I think there's some types of cookies or storage in a program that might be instance specific. And that shouldn't necessarily be shared across site instances. But there should also be room for more persistent things that can be shared.
You're referring to the cross-site request forgery attacks?
Possibly. That would be one way to defend against certain types of cross-site request forgery attacks. Yes?
Also, I think that the window-level JS calls are not imperfect isolation, but I think they are just the limitation of the DOM specification. You cannot get rid of this problem.
Sure. So this is something that, again, it's an example of how site instances aren't entirely isolated from each other. So the windows in different browsing instances can sometimes make calls that interact with just the window object. So this is like navigating the window to a different website. And that's something that, yes, it's sort of a limitation or something inherent to the DOM standard, which won't be going away.
The standard.
You could change the standard, but that would be, again, something that's harder to get deployed. So this is something that you want to support these sort of high-level calls between site instances in this case. And then there's the fact that, at least the way the abstractions are defined right now, this isn't providing a secure boundary between websites. And that's because we still do need to rely on the rendering engine within a site instance to provide certain types of security. For example, if you were logged into your bank in one site instance, Another site instance might be pulling in objects from that same website, and they carry your cookies. So the bank still thinks you're authenticated. So there's some information that can end up in a site instance, and you're relying on more subtle logic in the renderer to protect you there. And this is something I'd be happy to talk about more afterwards in more detail, and that I'm hoping to look at more in future, and has been looked at in some in related work as well. OK, so now that we have these abstractions in hand, we can try to isolate them from each other in the browser's architecture. And this gets at the fact that most of today's browsers have a monolithic architecture that put not just all web program instances, but all of their components in one process, including all the rendering logic, the HTML, CSS, layout, and so on, as well as things like the storage functionality for cookies, cache, stored passwords, user interface for the browser itself, the Chrome around the browser, and the network stack. So we'd like to do a better job than this by isolating some of these components into separate modules that can then be placed in separate OS processes. So from there, we'll end up getting all these nice isolation properties from the OS for free. We don't need to reinvent an isolation mechanism here. So what we end up with is a multi-process browser architecture. And here we can put some of the more privileged components inside a browser kernel module that acts similarly to an operating system that provides the resources that the web program instances need. So it provides storage logic, it provides access to the network, it provides the user interface around the web programs that you're using. But it doesn't need to handle any of the untrusted code from the web directly. We can also have a separate rendering engine module that can run in a separate process that handles both a web program instance and the underlying runtime environment. So it's the HTML rendering, the JavaScript engine, the parsing logic. All of that can live in a separate process. We can also carve out plugins, things like Silverlight or Flash, that don't need to run within the browser kernel and have isolation between them as well. I've actually had the chance to implement this architecture in 2 different projects. One was a prototype at the University of Washington based on a Linux browser called Conqueror, where I was able to carve out the rendering engine part of the browser into separate processes. And we have a technical report describing this experience. But this helped me to get involved with the Google Chrome project for building a new browser, which was released last September. And it has a multi-process architecture that I just described. And I was able to go in and help add support for isolating these program abstractions from each other, providing support for site instance isolation, including if you navigated a tab from one site instance to another, being able to switch between those in different processes. Now, what's interesting here is that we can actually support multiple process models within a given browser. In fact, all of the different compatible options that I mentioned can be supported. Within Chrome, you can do it just by specifying a different command line flag. So it's got a command line flag that can give you a monolithic architecture that loads all these components in the same process. This is actually useful for evaluation purposes. So you can see how it might have behaved, how much overhead or what properties it would have if it was monolithic. You can also have a process per browsing instance model, which is sort of the next implementation step. If you were building a multi-process browser, you might put each new window or set of connected windows in its own renderer process. From there, you can go on to support a process per site instance model, where even if you navigate one of those windows to a different website, you can swap it to an appropriate process for that site instance. And this is actually the default in Chrome, that if you don't do anything else, you'll be running a process per site instance model. And if you do a little extra work, you can actually support a process per site model, where you group all of the site instances from the same website into the same process. Now, this might be nice if you're trying to reduce the amount of overhead that you have, the number of processes. But it also will give you less isolation between the instances of each one of the programs you're using from a given website. So we found that the process per site instance model had the best robustness benefits and that the overhead was reasonable. So that was why it ended up as the default. Yes?
So the browser kernel controls the actual pixels. In other words, that in order to go from the rendering engine to the actual OS, you have to go through the browser kernel?
That's correct. The browser kernel is providing a way for rendering rendering engines to display things to the user. And it does it at the granularity of a bitmap. It doesn't know anything about what's running inside there. The rendering engine just ships a bitmap to the browser kernel, and it can be displayed on the screen.
And that wasn't a performance issue?
It actually works out pretty well. That it's the blitting operations are pretty quick. There's some shared memory that you can have between these processes to make it fast. So we didn't find that to be a constraint. OK. Now, there's a few caveats in the implementation here, and we hinted at those earlier. So there are some cases in Chrome's implementation in which pages from different sites will end up sharing processes. So, for example, at the moment, not all types of cross-site navigations will swap you to a new process. And there's some implementation reasons for that. We also haven't yet pulled out frames from their parent process if they're showing a different website. So if you have that attacker.com and it loads an iframe with CNN.com, it'll be part of the same site instance process. That's something that architecturally the browser could support, and that I'm hoping we'll get to where that can be supported. There's also a limit on the number of processes that Chrome currently creates. If you have more than 20 rendering engine processes, it will start reusing existing ones. So that's another reason why this isn't targeted at security right now. It's just trying to provide robustness in the common case. After that, they start getting randomly reused. So this is something, again, you could lift if you felt you had the resources to support arbitrary numbers of processes.
Without the frame, the implementation about iframe, then is there a benefit of this architecture when we consider same origin policy attacks? Because you can always visit there is always a chance that you visit an attacker site, right?
That's correct.
And then from there,
the attacker could always pull in a
target
page
site
from another site. So I'm not arguing that this architecture is currently providing ways to enforce the same origin policy. We'll see in just a second that it can provide other types of security, but not security between websites. And that's something that I think there's room for future work there. There's room to get to where that might be the case. Good question. OK, so let's look at how it can help in these other areas of robustness and performance. So first, we do end up getting failure isolation between web program instances. That if one of the web programs you're using crashes, you don't have to lose the entire browser. You end up with what Google has implemented as a sad tab icon for the program that you lost. And then the others you can keep using. And you can just refresh that tab to get back the program you're using. We also get better accountability. The browser actually has its own task manager now that can show you how much CPU and memory and network that each one of your web program instances is using. So you can track something down when the browser becomes slow or you start noticing your CPU usage being high.
Can you kill off?
You can kill them off. There's a button down at the bottom that you can't see right now because it's disabled, but it says end process. And then all those pages will just become a sad tab. This also has benefits for just the memory management of the browser in general, that if some web program instance allocated tons of memory and you wanted to get rid of it, the browser just has to throw out that address space. It's just killing the process. So it doesn't have to go back through the heap and find the objects that were allocated and free those. Now, it's also worth pointing out that you can get some additional security from this architecture. And we have a technical report describing this. I'm not going to go into too much detail here. But you can sandbox each one of these rendering engines to reduce the amount of privilege that it has. That they never need any direct access to the disk or to the network, the user's other resources locally. So you can make sure that the rendering engine processes need to go through the browser kernel to get access to that. So we're not isolating websites from each other necessarily because of the frame problem and some other issues. But we can at least say that web content is hopefully held within this sandbox. Question?
I'm curious how much you believe that sandbox. Would you let me run arbitrary x86 code inside the rendering engine process container?
So I think that the sandbox is designed to try to allow that sort of arbitrary code, but I'm not sure how much it's achieving that in practice. And I think that's sort of an open question right now. So maybe it could be improved. But I think there's room for a sandboxing mechanism in general in browser architectures to reduce this sort of privilege.
How does this sandboxing mechanism compare with low-write IE?
Yeah, it's a good question. So IE also has a multiprocess architecture that has a low writes mode for these processes. And the low writes mode, as I'm familiar with it, tries to prevent those processes from writing to disk, having access like that. But it doesn't prevent them from reading from disk. So that means that those processes could still go in and look for confidential files and leak those back out to the web. And Chrome Sandbox is trying to go that extra step further and prevent reading. Whether or not you could run arbitrary code in there, I'm not familiar enough to know. Yes?
What functionalities are in the browser kernel?
So the browser kernel is providing an API, a messaging API, to the rendering engines that is designed to be sufficient for rendering a web page. So it provides network, the ability to make HTTP requests, the ability to display images, which is, again, we're shipping over bitmaps, and the browser decides where to put them, to do storage for cookies and other things like that. It's sort of a limited API, and the full list of messages is online on the chromium.org website if you're interested in seeing what's there.
Like the direct access support is that browser kernel? Because
DirectX?
you're talking about having the rendering engine using a bitmap to communicate with the browser kernel. Then if I have a fancy graphics card that's using a DirectX, the Microsoft stuff, that basically you are sacrificing the performance, right? Because the rendering engine is not all the plugin, right?
That's right.
It's not going to leverage that fancy graphics card.
That's right. Being able to take advantage of hardware support or other devices is a challenge here. And maybe the browser kernel needs to have a way of exposing some of that. At the moment, some of the plugins that do take advantage of that are running outside the sandbox. So they get direct access. It's not great, but it's a good point.
So your rendering engines use any of the Windows rendering functionality, like GDI or fonts or anything like that, or is all that stuff implemented right inside the rendering engine?
I believe that's implemented in the rendering engine.
I mean, there's no reason you couldn't take those same bits and run them on any operating system, because your interface to the outside world is just a blitter.
Right, but you're still, yes. So the rendering engine inside there is using Windows features, like it.
It's using Windows features to render, say, fonts, in trim type and all that kind of stuff.
Yes, because
that stuff is like Sandbox is permeable in that way. And if there were a privilege escalation vulnerability in some library that Windows was using to render fonts or something, then you could go right through there.
That's probably correct.
Okay. I was trying to get a handle for how self-contained the rendering engines are.
So the rendering engine, yes, it uses Windows libraries, but it has a reduced security token that prevents it from accessing other types of resources.
Okay, thanks.
But it would still need to issue some of the Windows system calls to achieve some of those functionalities.
I believe so.
Oh, another question about the browser kernel is that what are the security decisions do you make in the browser kernel?
So the security decisions in the browser kernel are essentially trying to look at each rendering engine at a coarse grain and see if it's behaving in ways that it shouldn't. So we know that a web page from the internet, for example, should not be embedding images or resources from your local disk. That only pages that are fully loaded from your local disk should be able to do that. So the browser kernel can look at that and say, no, we're going to deny that request because we know this rendering engine instance is not allowed to do that. We'll have a separate rendering engine instance for files. There's a few policies like that.
So it's mostly to protect the local host from the browser, from the
Correct. Correct. It's a sort of second line of defense. It's not enforcing the same origin policy in the current implementation. Okay. On the performance side, we do end up getting performance isolation between these web program instances. So the other web programs can remain responsive while a given one is working. And we measured that by looking at the click latency in the browser. We ended up comparing the different architectures of Chromium for our evaluation so that we could look at architectural differences rather than implementation differences in browsers. So in the monolithic mode, we have a situation where if you are trying to time how long it takes for the browser to respond to a click, like a right-click menu, while the top 5 pages are loading in other tabs, or while Gmail is loading, you can end up waiting for several seconds on average. Because the browser is tied up running JavaScript code and rendering and so on. And that introduces just these hiccups into your browsing experience. And if you've ever used Firefox or other browsers while lots of things are going on, you may have noticed some of these hiccups. And in the multiprocess architecture, that's gone. You don't see any green bars here because it just takes 6 milliseconds to respond to a click, as you would expect.
I have a question. Sorry.
Yes.
Go back. I'm just trying to understand. So, I don't know. I started using IE recently. Okay, I just came here Microsoft. When I right-click my button in IE, it doesn't take 3 seconds with Gmail.
Right.
So what exactly is going on with the monolithic kernel that is so slow?
So the right-click example might be one example, but there are lots of cases where pages that are doing significant amounts of computation will cause other pages to respond slowly. And this is true even in other browsers. Now, IE is a different case, and I'll be able to talk about that some on the related work slide.
All browsers I use doesn't take 3 seconds when I click my right mouse button, so I'm not sure exactly what's the
When you're
case.
clicking, in the meantime, there's all this other stuff going on in other pages. That's what, like normally that's not true for you, but in this experiment, there were 5 other pages that were busy doing JavaScript, and that was introducing latency. So this isn't the common case. He's saying under certain circumstances,
Right.
they can
I see.
interfere.
Okay.
And what's the underlying OS here?
This is on Windows XP.
XP.
Yeah. OK, so there is some other impact on performance. Because we've introduced the opportunity for more parallelism, you can take advantage of multi-core machines more effectively. So you get concurrency between each web program instance now. It's not all running on the same thread. So for example, things like restoring a session of several tabs can be sped up significantly if each one is going to a different core. There's also some slowdown in terms of process latency. You've got to create a new process when you're creating a new tab or when you're starting the browser. And for a blank tab, we find that's about 100 milliseconds. But in fact, in practice, that's often masked by the fact that there's tasks that can be parallelized between the browser kernel and the rendering engine when you're rendering a real web page. So you often don't end up seeing this penalty at all. Yeah?
Why don't you just spin up a process, an extra process?
You could absolutely do that. That's a trade-off just between sort of time and space. So you've got more memory sitting around. And there's no reason you couldn't mask that entirely. You'd still see it if you were starting the browser from scratch with a blank page. Now, the real cost here is on the memory side. And this is where we're paying to have extra copies of each rendering engine and the caches that each one has and so on. So we found that when rendering realistic web pages, it just about doubled the memory use of the browsers. That with 10 popular pages, it went from about 65 megabytes to about 130 megabytes. And we think that this is a reasonable price to pay on most realistic machines today in terms of the other performance benefits that you're getting, especially given the types of responsiveness speedups we're seeing. We've also taken a look at the impact on compatibility. There's currently no known compatibility bugs that are due to this architecture. There's always lots of compatibility bugs on the web. But we don't think that they are introduced by this particular architecture. Google also has a distributed framework for testing versions of Chrome against the top 1,000,000 pages to try and look for compatibility problems. So they're actively looking for things like this. Now, there are some minor behavior changes that you get just whenever you change anything in a system. And one of them, in this case, is that we have a narrower scope for window names. That sometimes you can, another channel between windows is a window can establish a name and other browser windows can find it. Generally, that's a global namespace throughout the browser. But the HTML5 specification says that browsers can sort of determine the scope of these names appropriately. And we've narrowed it to within a browsing instance. So you can find a window of the same name within your browsing instance now. And that will only affect sites that, for example, like Pandora, where you open a music player window from a given web page. And then if you went to a separate instance of the Pandora website and tried to open it again, It's a question of would it refresh the existing player or would it open a second player? And we actually think that the latter is sort of more logical because they're independent to begin with. But that's one change that was made. There's been some related work in this space. It's sort of exciting to see how much is going on here. IE8 is also introducing a multi-process browser architecture that puts different windows in different processes. But there's not an attempt to try and identify a program abstraction here. So there's cases where related and communicating pages will end up getting put in separate processes. Now, they've gone ahead and implemented support for JavaScript calls between these. But they're on different threads, which means that you can introduce race conditions between different parts of programs running in JavaScript. And JavaScript is a language without any concurrency primitives. So you're creating real problems for programmers. The Gazelle browser here out of Microsoft Research is proposing actually sort of a similar architecture of carving up the browser into different program instances. But they're looking at trying to provide secure isolation of websites. And sometimes to get there, you have to look at the features on the web that we don't want, that are causing problems that we would like to go away. And Gazelle is saying, hey, if these were gone, we could have a very good security story for the browser. And we may be able to get here, even in a compatible sense. But I think that it's worth exploring both of these directions to say, where could we get with security, and where can we get today with the stuff that's out there on the web? There have been some other research projects that have also looked at modular browser architectures, including OP out of Illinois, Tahoma out of UW that looked at having separate virtual machines for web programs, and the SubOS browser that are all looking at trying to carve up the browser into different pieces, but without as much emphasis on supporting today's web content. OK, so to summarize this part of the talk, we've seen that browsers need to do a better job of supporting the programs that are out there on today's web. But to do that, they need to recognize what a program is. And we've introduced the site instance abstraction to capture this in a way that's compatible with today's web content. And once you have this abstraction, you can then isolate these with OS processes to prevent interference between programs. OK, so now I'm going to give a much briefer overview about web tripwires. But before I go on, we can take questions about this part of the talk. Yes?
So Chrome is a big project, obviously. It's the work of many people. Can you visit
That's right.
for which parts were your contributions to it?
I can, yeah, sort of a general sense. So the Chrome engineers were working on a multi-process architecture. And I helped to do essentially some of the stuff that I described in this talk about identifying the abstractions for what a web program is and supporting that within the browser's architecture. Any other questions? All right. So now we can take a look at things from the publisher's perspective. Now that we have some idea about what a web program is, how can we do a better job of supporting that, say with some simple integrity checks for programs? And when we're thinking about a site instance, we now know sort of what the boundaries are, but can either users or publishers trust what's running within that? And as we all know, most web pages are sent over HTTP, which is a plain text protocol that can be modified in flight. And what's interesting about this is that if one of these changes happened, that change becomes part of the site instance, becomes part of whatever's being governed by the same origin policy in that web program. And so, for example, if an internet service provider had looked at the page and injected something like an advertisement into it, that would become part of the site instance that the user's running. Now, is this a concern in practice? Well, we did a measurement study that actually says it kind of is. We looked at 50,000 different web clients, and we found that over 1% of them reported that a web page was changed in some way before it got to their browser. So we were pretty surprised by this. And we saw a variety of different things that you might not want to see happening to web pages, including injected ads, injected exploits, and changes that either broke web pages or introduced security vulnerabilities. So it's stuff that people might want to know about.
How do you identify an implied change?
This is exactly what I'll get to on this slide. So yes?
Can you tell who, you can't tell who actually injected it, you're just looking
Not
at
concrete.
evidence?
Yes. So we know that it happened between, and there's often enough evidence to narrow down what made the change. It could have been faked, but we think that we can generally narrow down what caused the change in many cases. OK, so the way that we detect this is we realized we could put a piece of JavaScript code on a web page on a server, and then ship that to the client's browser to do an integrity check. And this is what we call a web tripwire. We ship that to the client's browser, and it looks at the HTML source code of the page that arrived and compares it to what was expected. So, for example, if an internet service provider had injected an ad, we'd see some change to the HTML, and we could display a message to the user, as well as sending the change back to our server for our measurement study. Now, we put this online at a website called vancouver.cs.washington.edu. And it's still online. The measurement study was about 2 years ago, but you're free to go to that if you want to test whatever network you're on, see if things are being changed. But we wanted to use this for a measurement study. So we wanted to get a view of lots of different users on many different networks to see if pages are being changed in some situations and not others. So we ended up getting this posted to Slashdot and Dig and a couple of other news outlets. And that drew in sort of a flash crowd that gave us a good measurement study. So we had visits from 50,000 unique IP addresses, and that was over about 2 weeks. And 653 of those reported some change back to us. So we were pretty surprised to see that many. We were sort of expecting maybe we'd see a handful. But to see over 1% of people having some sort of change was pretty surprising. So I just want to give you a brief sense of the types of things that we saw. It was injected by many different types of parties. For example, we did see some internet service providers that were injecting ads. Some of these were on free wireless networks, where the network is supported by ads that users view within web pages. Some of them are done by ISPs that work with companies like Nebuad, or possibly Form in the UK, that inject targeted advertisements to users based on their browsing history. And they're doing this by looking at the web page and then injecting a targeted ad, or looking at the user's browsing history. We saw some evidence that some firewalls were injecting security checks. So maybe there's positive changes you can get out of this as well. So there's products like Blue Code Web Filter that try to enhance security of the enterprise by injecting JavaScript code into web pages.
What do they do?
They look for suspicious behavior. So a page that might try to spoof the address bar, for example. And if they see evidence of that, they'll pop up a message to the user saying, you probably don't want to trust this page. And maybe they report that back, but it's tough to tell exactly what they do. We saw some injected exploits into our page, which we found were consistent with reports of ARP poisoning, where some infected client on the user's local area network was sending out ARP requests saying, I'm the router, send all your traffic through me. And that means that when the user requests a web page, that infected client has a chance to inject exploits into it and infect other clients on its local area network, which was kind of scary. We've actually heard reports of this happening in server rooms as well, where something on the local area network of the server sticks itself between the server and the outside world, so all outgoing pages get exploits injected. And finally, we saw evidence of lots of user proxies. So this is software that the user obviously knows about, designed for things like blocking ads or pop-ups. And this is accounted for about 70% of the changes that we saw, so it's a big portion. But what we found was that even these sort of well-intentioned changes can have some negative consequences. And in fact, these are where we ended up seeing bugs and security vulnerabilities introduced. So we saw some pop-up blockers that introduced bugs into certain web pages. For example, web forums. You can find many comment boards on the web where the user's comment is preceded by a little bit of garbage JavaScript code. And that's because the pop-up blocker they were using was injecting JavaScript code into the wrong part of the web page. It was injecting it into the comment form on the forum. And so that got copied into the website and displayed in the user's posts. You can actually find some sort of amusing posts online where users are like, why is my computer putting garbage here? I don't understand it. Unfortunately, we also saw some more severe problems, including vulnerabilities introduced into web pages based on the ad blocking and pop-up blocking proxies the user had installed. So for example, we saw a program called Proxometron and a program called AdMuncher that both injected ad blocking JavaScript code into each web page that the user visited, or most web pages. Now that code was vulnerable to a cross-site scripting attack. And that was because it copied the URL of the page into the body of the page itself. And the URL is something that an attacker has influence over. An attacker might send you a link to a web page with some code at the end of it, or they might redirect you from a web page. And when the user visited that page, the proxy would copy the URL into the body, and then that code at the end of the URL would run as part of the page. Now, the interesting part about this is that the victim of this attack is whatever page the user happens to be looking at. And in many cases, that was all of the pages that the user visited. These proxies would often modify all of the user's web traffic, if not most of it. And so in the world where browsers are acting like operating systems, this is sort of like a root exploit. Suddenly, every program that you're using becomes vulnerable to an attack. So it's a pretty severe problem. And we were able to report these vulnerabilities to the proxy vendors and had them fixed. But it's the sort of thing that you have to be very careful when you're modifying a program on the fly not to introduce security problems. So what can publishers do about this? Well, you could just switch to HTTPS. You have confidentiality and integrity for your programs. But we recognize that that's not necessarily a practical solution for every website on the internet. So one alternative is to deploy something like a web tripwire on your own page, which is just a lightweight piece of JavaScript code that does this integrity check. And it's very easy to deploy.
That's an arms race, right? Then they'll start modifying tripwires as part of the inside modification.
That's right. So it's not cryptographically secure. It's not as good as HTTPS. But you could at least obfuscate the tripwire to make it difficult to detect on the fly. It's an arms race there.
Down the road with spam, right? I mean, it never ends.
Mm-hmm. So the flip side, or another aspect of that, is that it's not necessarily an alternative to HTTPS, and that you're not preventing these changes, right? You may be able to detect when they're happening, but it's something that the publisher could know and maybe notify the user, this isn't what I wanted. Right. So HTTPS is, if you're very concerned about the security of your program, you should be using that. I don't want to imply that this is an alternative to HTTPS. Now, if you're just looking to detect these things, we do have a toolkit that can help you deploy a web tripwire on your page. And we have a service that all you need to do is just include a line of JavaScript on your web page. And the tripwire will be fetched from our server. And we'll have a reporting interface for publishers to see how their users' pages were changed in flight. OK, so to summarize this, we found that it's not safe in general to blindly patch the code of a web program. Just like you wouldn't blindly patch a binary installer without really knowing what you're doing. Unfortunately, there's many parties with incentives to do so, and it is happening on today's web. And you can at least tell when it's going on, in most cases, using web tripwires. OK, so finally, I want to give just a brief summary of other work that I've done, both in the browser space and elsewhere, and talk about some future directions. So I've also worked on the BrowserShield project here at Microsoft Research, which is designed to block exploit of known browser vulnerabilities. And it does this by interposing on web content within the browser. That's right. As it turns out, we implemented this as a proxy which modifies pages in flight. So it's something that is looking at web content. And we did that mainly for the deployability story. So this is something where you could also deploy it on the server to try and rewrite pages there. Or you could deploy it within the browser itself, where the browser really has the context of what's going on. And in fact, we've seen that it's gone on to help influence the Live Labs Web Sandbox project, which is trying to enforce policies in a different way, but it's doing it on the server side. So the server knows what's going on in the page and is doing some rewriting. But the goal of it in general is to rewrite web content to enforce flexible policies. And BrowserShield used that to prevent exploits of vulnerabilities. Before I got into the browser space, I've also done some work in wireless networking research. So I looked at some low-level 802.11 behavior from traces at SIGCOMM. And I've also looked at how you might be able to predict wireless behavior on a static network based on previous measurements. That appeared at SIGCOMM in 2006. And when I was at Rice University, I did some computer science education research on the Dr. Java development environment, where we had undergraduate students maintaining a shipping product or learning production programming practices by maintaining something where they had to fix bug reports and add feature requests to things that was in use at introductory courses at other schools. OK, so finally, I just want to wrap up with some future directions that I could see heading in. I think there are actually lots of opportunities to have secure isolation of websites in a compatible way. And I think that both Chrome and Gazelle are exploring this space in very interesting ways, and I think there's ways to move forward here. But I think all of this sort of fits in this theme of doing a better job of supporting programs within web content web browsers. I think there's also a need for better ways to understand what it means to be compatible on the web. That it's not necessarily just that you change the rendering of a page or that you've introduced a JavaScript load on error, or on a JavaScript error on load. There's bigger questions about what features do users rely on and so on. So, do we need benchmarks? Do we need larger surveys? There's interesting problems there. I think there's lots of cool opportunities for opt-in mechanisms for how you might let publishers provide more information to the browser to let it enforce more interesting policies. And maybe even be able to get away from things like the same origin policy in certain cases to do a better job of saying, here's what my web program is. And then maybe being able to do things like BrowserShield style interposition within the browser itself to enforce policies on how things behave. Longer term, I think all of this is getting at where applications and network applications are headed. That we've got a world where we have some understanding of desktop applications now and then very sandbox web applications. But what will that look like? And how will browsers and operating systems support these? What APIs do they need? What services do they need? What isolation mechanisms do they need? And in that sense, how will the trust models change? That if a program coming in from the web wants access to more storage or more devices, can we grant that to certain web programs without everything and ways that users might understand? There's very big challenges there. And all of this ties into my interest in just finding ways to design robust and secure systems in general. So with that, I'll conclude the talk. I think the web is becoming a very interesting application platform that is giving us chances to figure out how applications should be supported. And it requires changes to both browser architectures and the way that web content is defined. And I think it's really sort of an exciting opportunity to be working in this space where the web is starting to change and browsers are changing, where we get a chance to define what that will look like. So thanks, and happy to take questions.
So I have two high-level questions. First question is, when I came in, I looked, the title of your talk is how to make the web more safer. And when I talk to people, when people look at the problems with the web, robustness and performance are not at the top of the list. And your entire talk was about robustness and performance. So I had a hard time reconciling how you, from making the web safer, you kind of got to robustness and performance as being the right goals for it.
So I think that, so I think robustness and performance are absolutely part of safety. The things that are on people's minds now are probably things like phishing and security exploits and so on. And I think that there's certainly room for security improvements there. And some of the work on browser exploit prevention, trying to prevent cross-site scripting attacks, are getting at that aspect of it. But I think looking at robustness issues in particular are looking at this inflection point about where we're looking at programs are becoming more popular. As you get more and more programs, what are the problems going to be in the browser space? And we need to do a better job supporting these before users are like, geez, all of my programs are always crashing because I visit some page with an ad and it just takes the browser down. So being able to provide a safer platform for programming also includes providing isolation between programs.
I think in this sense...
Can I ask my second question?
Yeah.
Thanks. My second question is, you started by saying, what we need to do is basically take the browser and make it look more like the operating system. It struck me as, I don't know, I'm not very happy with my operating system. All sorts of problems. So, I want to have you kind of tell us exactly why that's the right approach. Or maybe why not just look at the operating system and actually, forget about the browser, make the operating system kind of support the application that the browser does. Why is turning the browser into the operating system the right approach here?
So I agree with you that it may not, turning the browser into the operating system isn't necessarily the goal. I think that part of the goal is learning from the operating system and the things that it's done well and getting those properties in the browser space. So for example, we're not trying to invent a new isolation mechanism, like a new type of process for the browser. We're saying that the OS can provide that to us. And I think there's room for this evolution where the OS and the browser are both providing this platform for running programs. And they both really need to reflect these changes. So, for example, some of the changes in the trust models, the OS might be a better place to consider how you support these programs. So I think there's needs to change both of them. And the browser space is the one that is where you can start and get the most benefit right now.
Okay, so you're saying that that's how we did it, basically. And
Well,
it's a nice starting point.
Well, yes, but I'm also saying that
this is the right way.
No. What I'm arguing is that I'm not saying we need to turn the browser into an operating system. I'm saying we should learn from the things the operating system has done well and get those properties in the browser. It's very different from saying the browser should re-implement its own operating system on top of the operating system.
So, the sense is that the web as an application platform is evolving, and that it's, we're kind of early on. Can you give us a couple senses? One is, what's your sense of the where the really exciting new developments in web applications are? So, what are some examples of those? And the other thing, I guess, is, do you see like the rate of change? Are they getting more and more interesting quickly? Are they kind of plateaued out at Gmail? With your Gmail, Gmaps, or Map.Google are the best thing we'll ever see. What do you?
Yeah. So I think in terms of the trends where we're heading, I think that things are sort of accelerating here. For a long time, we've hit this plateau about what you can get into the browser and run. That maybe Gmail was just sort of pushing that envelope, and it was this big chunk of code running within the browser. But we're starting to see the browser wars be reignited, and you're seeing faster JavaScript engines. You're seeing more support being added for new features, like post message, for example. And so we're starting to see applications that get the ability to use more features. And that's where I think the really interesting things are just starting. I think in terms of offline access, in terms of access to certain devices, there's certain web applications that are saying, we want just that little bit more. We want access to your webcam. So here, install a browser plugin. Or, let me out of the browser sandbox in this way. And there's a question about, what does the browser need to provide for these applications that we don't really know yet? And can we do that without giving up all of the trust that we currently understand about the web? So I think in that sense, things are accelerating. And we're starting to see applications start to take advantage of that.
I agree.
Thank you, Hal.
Actually, I was trying to add a comment, which is about the title, the word "safe."
Yes.
Usually, that means quite different thing versus liveness, right? So in this
Charlie
talk,
has also done work in BrowserShield and as
but this talk is more on the liveness side than safety, right?
Well, so in casting the talk, I'm trying to capture the work that I've done in my dissertation, which has included work in both the security side and robustness, and keeping programs running safely.
Okay. Well, with that, let's thank our speakers.
So thank you very much.